So on page 101 of our textbook, our OER textbook, Business Calculus, you'll find a diagram to show us the different building block rules for taking derivatives of functions. And at the bottom, you can see there's rules for exponential functions as well as for natural logarithms. So if we take the derivative of e to the x, well, the derivative is just e to the x. If we have, one thing it doesn't show here in our book, or at least not on this page, is if we have our exponent is actually a function, then we use the chain rule. We'll take the derivative, we'll just write down the original function, and then take the derivative of that exponent. Okay? And then also for natural logarithms, let's go ahead and call this exponential and logarithmic functions before we go and do some examples. So if we are taking the derivative of a natural log, ln of x, and we want to put that in parentheses as you see in your textbook because you're taking the derivative of the whole quantity, it's going to be 1 over x. Let's go ahead and get ready to do some example problems. Students, let's do a few examples of finding the derivatives of exponential functions. So let's look at this first one. So f of x is equal to x squared times e to the x. So notice it's a product. So we need to use the product rule here. We have a product of two functions. So we'll take the derivative of the first times the second plus the first times the derivative of the second. And again, the order doesn't matter here because both addition and multiplication are commutative. So as long as we do this, just use our product rule, we can use it in multiple different ways and we would still get the same equivalent correct answer. So as I wrote it here, let's go ahead and call this f and this part g. All right? So we'll take the derivative of x squared, which is 2x, times e to the x. And then we'll add to it x squared, which is f, times the derivative of e to the x, which is just e to the x. And we'll want to simplify. So that's our derivative. What do you see that's in common with both of these terms, this term and this term? Well, I see an e to the x. I also see that there's an x that's common to both. So I can factor out both an x and an e to the x. Think of it when you're factoring out, it's like you're dividing the term by these factors. So if we remove an x or divide out an x from 2x e to the x, that leaves us 2. And then dividing out the e to the x, that leaves us 1. So 2 times 1 are just 2. And then plus, we factored out an x out of x squared, leaving x, and then factored out an e to the x, leaving times 1. So it's just x. So 2 plus x is our quantity inside our parentheses. And that's our simplified answer for our derivative of this function. Let's go ahead and look at problem number 2. So f of x is equal to x divided by e to the x. So what do you think we have to use here? The quotient rule. So call this part of it f and this part g, like we did before. So we have low times the derivative of the high, so g times f prime, minus f times g prime, the high times the derivative of the low, divided by the low squared. Low d high minus high d low divided by low squared. So we'll take g, which is e of x, and this is going to be our derivative of the function f prime of x, is e to the x times the derivative of x, which is 1, and I'll put it in there just to show my work, but I won't need it in my final answer, minus my function in the numerator, x, times the derivative of e to the x, which is just e to the x, all of that divided by e to the x squared. And I'm going to go this way and simplify it a little bit. I can factor out an e to the x, leaving 1 minus x here, divided by, and I can simplify my exponent and my power here. I multiply them, so it'll be e to the 2x. And I can simplify a little bit further because I have an e to the x here and I have an e to the x here, 2x. So that would leave me, because this would be like e to the x times e to the x, and I'm taking away one of them. So therefore, I'd be left with e to the x. So our final answer here for this problem, f prime of x, is 1 minus x divided by e to the x. Let's look at this third one. So f of t is equal to 5e raised to the 3t plus 4 power. So to get the derivative, we'll write down the function, 5e to the 3t plus 4, and then times the derivative with respect to t this time, not x, of the exponent of 3t plus 4. The derivative of 3t plus 4 would just be 3. So I'd have f prime of x is equal to 5e to the 3t plus 4 times 3, or simplifying it a little bit more, 15e to the 3t plus 4. And let's box that in. So now let's do some examples of derivatives of logarithmic functions. So if you remember from a previous video, the derivative with respect to x of natural log of x is just 1 over x. Now, one thing we have to clarify, if instead of just a variable, we have a function following that natural log, here's what the form is to take the derivative of that natural log. So it would be f prime of x, whatever that function is, take the derivative of it, divided by the original function here, following natural log. Let's do a couple of examples. So we have here, and I'm sorry for the duplicate name, let's call it h of x, just to help us not to be confused. All right. So h of x in this first example is natural log of x squared plus 1. So the first derivative, h prime of x, will be the derivative of x squared plus 1. Let me write out a little bit of work. Divided by x squared plus 1, f of x, which is what's following the natural log. So we'll have that h prime of x is equal to 2x, the derivative of x squared plus 1 is 2x, divided by x squared plus 1. And that is our final answer here for this problem. Remember, we cannot remove the x because there's no x in the 1. The only way we can remove variables is if it's a factor of every term, and then to factor it out and then find the number of that variable in the numerator and denominator to remove, or to cancel out, as some say. All right, let's look at problem 2 here. Now, we're going to do it in a similar way. We're going to take the derivative with respect to x of our function, f of x, what's following the natural log, which is 2x over x plus 1. And then we're going to divide it by the original function here, 2x divided by x plus 1. We have a little bit of work to do because we have to use the quotient rule to get this derivative. And let's do that right now. Okay. So low d high, so it'll be x plus 1 times the derivative with respect to x of 2x, which is 2, minus high 2x times the derivative of the low, x plus 1, the derivative of that is just 1, divided by the low squared, x plus 1 squared. And let's simplify a little bit more. So distributing this 2, we'll have 2x plus 2 minus 2x divided by x plus 1 quantity squared. We have 2x minus 2x, which is 0. So we'll be left with 2 divided by x plus 1 squared. So our h prime of x then is 2 divided by x plus 1 quantity squared. All of that divided by our f of x, 2x divided by x plus 1. Again, we have here a complex fraction. We can't just leave our answer. We need to simplify it. Think of it as a fraction divided by a fraction. So how do we divide fractions? We take the first fraction, 2 divided by x plus 1 squared, and we multiply it by the reciprocal of the denominator fraction. So we'll be multiplying by x plus 1 divided by 2x. So there's a few things I can remove here. I see that I have a 2 in the numerator and a 2 in the denominator. I also see that I have a factor of x plus 1 and a factor of x plus 1 in the denominator. That would leave me a 1, just one copy of x plus 1 here. And anytime I remove a factor, that leaves me a 1. That's important here because it looked like there was just nothing left above the division bar, which is not true. It's 1 times 1, which is 1. And then we have x times x plus 1. Or you can write it as 1 divided by x squared plus x. Either answer would work for me for this derivative. I hope that helps you, students. Bye.